So today we have lecture number 18 of course ME314 Fluid Mechanics 2, and this is the third lecture of this week. We are already working on potential flow, and we have done the basic potential flows, in which uniform flow, source and sink flow, vortex flow we have done, and then we have superimposed, and the last topic we did was by superimposing the source and the sink at a particular condition, when the product of the source and the distance between them is a constant, then result into a pattern called doublet, and we have developed expressions for the stream functions and velocity potential functions for the doublet. Today we will go into the flow over a cylinder. So by combining the doublet with the uniform flow, we will end up with the flow over a cylinder. And then we will work out the velocity distribution and the pressure distribution in that. And we will work out the forces acting in horizontal and vertical direction. We call it drag and lift, when there is a fluid flow taking place over a cylinder. Then we will go into Rankine body, and we will solve problem based on Rankine body. So this is today's lecture content. Okay, start with the flow that takes place around the cylinder can be represented when you have superimposing the doublet with uniform flow. So you have a uniform flow on the left hand side, and you have a doublet with the strength of the doublet is K, and if you combine them together, so it would be a situation like you have a cylinder of radius A, and there is a flow over the cylinder takes place. So you can think of this as actually the cylinder in the Z direction. So uniform flow combined with doublet end up with the flow pattern that is something like you have a cylinder, and fluid is moving over the cylinder, and these are the streamlines, and you can see the streamlines here are much closer. So we expect here the spacing between the streamline is small, so we expect there is a higher velocity and obviously the lower pressure here. So now let's work out their corresponding stream functions. So we know simple rule for addition takes place when you superimpose two flows. So you have a uniform flow, so there is a corresponding stream function for uniform flow, and there is a stream function for doublet, and combine it together to get a stream function for flow over a cylinder. So this is the stream function for uniform flow, and this is the actually this is a particular type of uniform flow which is in a straight line, and we usually call it, sometimes we call it a rectilinear flow. So this is the stream function for a doublet, and we have written in this polar coordinate system where our origin is at the center of the cylinder, and R is in the radial direction, and at a certain streamline which acts as a solid body. So that streamline would act as a solid body, and that would be the radius of the cylinder. And we will look into the, okay, by taking common here, r sine theta is taken common, so you got u infinity minus k over r square. So this would be the corresponding stream function. Similarly, we can work out velocity potential function. So combining the velocity potential function uniform flow and for doublet, and taking common, we got this velocity potential function for the flow over a cylinder. So once you know these two things, we can easily work out the velocity components, and we can easily calculate the magnitude of the velocity, and once we know the magnitude of the velocity, we can work out the pressure distribution. Okay, let's look at this problem more closely. Let's say this is the stream function for this flow pattern when your r is equal to some distance, we call it a radius of a cylinder. So we assume that there is a streamline which act as a solid body, and the value of the stream function, we are assuming it at that boundary. We have a convention of assuming it 0. So if I just substitute 0 here in that stream function, what I'm going to get, and instead of r I substituted a, because at that surface which act as a solid boundary, the r is equals to a, and sine theta is there, u infinity minus k, and instead of r I just substitute a square. So this product come out to be 0, and how this product come out to be 0, there are three possibilities. Either a is 0, but from the geometry we know a is not 0, or either sine theta is 0. So if sine theta is 0 at different values, like when theta is 0, or theta at 180, and so on, at different values of theta, sine theta could be 0. Since there are different set of values, so actually what is 0 is the term in the bracket is 0 in order to make that product 0. So eventually we say that this term u infinity minus k over a square is equal to 0. So we have a relationship between the strength of the doublet and the magnitude of the free stream velocity and the radius of the cylinder. So if you want to have a bigger radius of the cylinder, obviously for a given uniform flow we need to have a higher strength of the doublet. So if this cylinder to be taken as a small cylinder, then we can work out the same thing using the smaller magnitude of the strength of the doublet. So this is how these parameters for the basic potential flow link together. Okay, so now just substituted back k, instead of k I can write u infinity times a square, and then we can further simplify our stream function. So my stream function for this resultant flow would be u infinity r sine theta times 1 minus a square over r square. So this is the stream function when you're assuming that r is a, and once r is a, that is you are at the radius of the cylinder, then this equation holds. Okay. Similarly, we can work out the corresponding velocity potential functions once we substitute capital K equal to u infinity times a square. So we will end up with the velocity potential function like this. Okay, so if we are interested in the velocity distribution, so we have a knowledge of both stream functions and the velocity potential functions, then the life is simple, because we know by differentiating phi with respect to r, we can easily get the radial component of the velocity, or vice versa. If you have a stream function, you differentiate it with respect to theta, and 1 upon r, you will be able to get the radial component. So here the easiest thing is you have the stream function. If you differentiate with respect to theta, and or you differentiate phi with respect to r, so you are going to get the velocity component in the radial direction. Similarly, we can get a velocity component in the tangential direction, as we know that tangential direction, the phi should be with respect to theta and psi should be with respect to r. So just differentiating either of those expressions, eventually you got those radial component of the velocity and the tangential component of the velocity. Okay, let's look at more closely the distribution of the velocity. So as we see, this is origin, this is theta is 0 here. As we move onto the surface of the cylinder, in this direction theta increases, So when theta equals to 180, you end up with the same stagnation point. So we have the knowledge, we can easily work out where the stagnation point are going to lie. So velocities are such uh, that this at this point, at this location, the velocity should be zero, because that is the stagnation point. So we say on a surface of that cylinder, when your radius equals to a and your radial component of the velocity, because there is no radial component of the velocity at both locations, the so-called stagnation points, we say that the tangential component of the velocity would be, the radial component would be zero, because there is no flow outward coming out or inward. So we say that the tangential component will be the velocity which is actually at the surface of the cylinder. So v theta is the tangential component, the subscript s is representing the surface. So we say when r is a, tangential component of the velocity is v theta s. So you understand that this tangential velocity at the surface of the cylinder. So I can easily work out, just substituted here r equals to a, and so a square plus a square would be 1, 1 plus 1 would be 2. So 2 minus 2 u infinity sine theta would be the expression for radial tangential component of the velocity at the surface of the cylinder. So as you see, as theta changes, the magnitude of the velocity at the surface changes. For example, when theta is 0, sine theta would be 0. So 0 multiplied by whatever free stream velocity is, your velocity would be 0. Or if theta is 180, so sine 180 would be 0, you have a 0 velocity. And when your theta is 90, you are at the top of the surface of the cylinder. So just substituted theta equal to 90 here. So sine 90 would be 1. So the magnitude of the velocity at that point would be 2u infinity. So that would be 2u infinity is the velocity at the top of the cylinder. Or even if you put theta equals to 270 degree, you are going to get this magnitude of the velocity. So we can work out velocity at any position over the surface of the cylinder from this expression. The maximum velocity we have learned, either if you take theta plus pi by 2 or minus pi by 2 or theta 270 degree, whatever it is. So minus pi by 2 means clockwise, plus pi by 2 means anti-clockwise. So your maximum velocity at that point would be twice of the free stream velocity. And obviously as we move in the y direction, the velocity is going to decrease, and if you go away from the surface of the cylinder, so the velocity would be the same as the free stream velocity. So and this is what we expect the velocity at the surface, because here at the surface on the top of the cylinder, velocity is twice of the free stream velocity. So once velocity is higher, and that is being represented by the closely spaced streamlines, and obviously the pressure would be decreasing here. Since the velocity is 0, so varying from 0 to 2u infinity, minimum velocity is 0 at the stagnation point, and maximum velocity is twice of the free stream velocity. Once we know the velocity distribution, we can easily work out the pressure distribution by employing the Bernoulli equation. So this is the velocity at the free stream condition when it is at uniform flow, and there is a corresponding free stream pressure. So that would be equal to pressure at the surface of the cylinder plus half rho and velocity at the surface. So at the surface there is a tangential component of the velocity is v theta s. So we can easily work out the pressure distribution. We can substitute this expression from the earlier slide, that the tangential component at the surface of the cylinder is minus 2u infinity sine theta. So we substituted here, So V theta S would be this thing. Now simplify this expression. So if you simplify 2 u infinity 4 u square sine square theta, and since half rho u square, half rho u infinity square is common here, taken out common. So from this expression we can work out the pressure at the surface of the cylinder. And what we have learned, pressure as the velocity is varying as a function of theta, similarly pressure is also a function of theta. As theta changes, the pressure at the surface changes. And if you plot the distribution of the pressure, it looks like the free stream velocity is u infinity. So here the velocity is 0, so pressure is maximum. Here the velocity is 0, the pressure is maximum. And if you go to the top where velocity is maximum, so the pressure is minimum. And the same pressure, minimum pressure is here. So that would bring some typical pressure distribution. Okay, what we can do is we can write this expression into this form. So the difference between the pressure divided by this dynamic pressure. So as you know, Ps minus P infinity divided by half rho u infinity squared. So this would be the static pressure, and this would be the dynamic pressure, and the ratio between the static and the dynamic pressure is called pressure coefficient. And from this flow over a cylinder, as we have worked out by combining uniform flow with doublet, what we learned is that pressure coefficient is only a function of 1 minus 4 times sine square theta. So if we are able to plot, so the next thing we are going to plot Cp on the vertical axis and theta is on the horizontal axis. So this is the theta 0 here. So pressure coefficient would be 1, because when theta is if you substitute 0 here, sine 0 would be 0. So the whole thing gone. So you only end up with the pressure coefficient equal to 1. Similarly, if theta is 90, sine 90 is 1. 1 minus 4 would be minus 3. So minus 3 would be the pressure coefficient. So what we see here is on this side you have a higher pressure, and on the other side you have a lower pressure, and this pressure difference forces the fluid to move over the cylinder. Okay, so we can see that the flow over a cylinder, so their pressure coefficient would be some function of the angle at the surface of the cylinder. So our inviscid flow theory, what we call it a potential flow theory, predict this type of behavior, which is quite symmetrical. So once you have a cylinder and flow over a cylinder is taking place, and we see this typical symmetric, you see if you just take a half here, whatever the distribution on the left hand side, the same is on the right hand side. Or if you make it a half by drawing a horizontal line, so whatever the pressure distribution on the above the surface of the cylinder, the same is this below. They are perfectly symmetrical pressure distribution over the surface of the cylinder. I mean, obviously we have plotted from 0 to 180 degree, so it is actually on the half of the cylinder, and similar would be on the from 180 to 360 as well. So in this diagram it is only plotted from 0 to 180 because the above half is same as the bottom half. So only the one of the half is plotted here. If you see this theoretical curve, it is perfectly symmetric. But if we see the actual curve, which from an experiment, and we see up to angle from 0 to up to 40 degrees, both lines are coinciding. So theoretical, which is coming from inviscid flow theory or potential flow theory, that is being followed by the experiment. And as we are moving towards the maximum velocity region or top of the surface, the pressure coefficient departs from ideal condition, and you have this, and then further deviation from the inviscid flow theory. And obviously the reason is inviscid flow theory, we are not taking into account the effect of viscosity, but there is some friction over the surface of the cylinder, so that's why the pressure coefficient in the experiment is very much differing from the inviscid flow theory, from the potential flow theory. And we can see here in this diagram as well. So this is a flow net drawn over the cylinder. So you have a cylinder of radius A, and there is a uniform flow, and the blue lines are the streamlines, and the dashed lines, which are black in color, are orthogonal to the streamline, that would be the constant velocity potential lines. So these would be the constant phi lines, and these would be the constant psi lines. And at the surface of the cylinder, we have assumed that the psi value of the psi is 0. So this would be a typical velocity distribution. Streamlines would pass through the surface of the cylinder and move exactly in the same manner as it is approaching, in the same way it is leaving the surface of the cylinder, from the top side as well as from the bottom side. So there is no meaning of drawing streamlines within the cylinder, because this streamlines which is at the surface of the cylinder is actually act as a solid body. So fluid is flowing over the surface of the cylinder. So even though it is drawn, but there is no meaning here. And r and theta is represent any position in the space. You can work out what velocity could be at r and theta. What would be the real flow? Real flow looks like the approaching half is almost the same, but once it approaches towards, then the flow separation takes place, and vertices at the behind the cylinder develop. So streamlines would not be just following the contour of the body, but they are deviating, they are separating. So this is actually called flow separation. And when you will go into the boundary layer theory, we will go into detail about that real flow. So right now we are talking about the potential flow. Okay, now let's calculate the drag and the lift force. So as you know, the pressure distribution is something known. So the pressure at the surface of the cylinder is PS, which is this pressure. So we know the velocity at the surface. So we need to calculate the resultant force. So this pressure would be acting in the horizontal direction as well as in the vertical direction. So what I have done is, if this surface pressure is integrated over the whole surface of the cylinder, I am going to get the obviously multiplying by the area. Pressure times area would be the force. So I can get the drag force because by convention I have taken positive in the x direction. So once the flow is approaching to the cylinder, so the drag is actually in the opposite direction. That's why we have a negative sign. So what I have done is the pressure multiplied by the area. So it would be that arc length. If this is A is the radius, and A theta would be this arc length. And arc length multiplied by the z dimension, which is the width of the cylinder, the depth of the cylinder. So that would be unity here. So that would be your area, and area multiplied by pressure would be the force. So, and if you just substitute here, I mean, I advise you to do it by yourself. Just substitute the expression of PS, the whole thing here, which is a function of theta. And obviously P infinity is a constant, and if you integrate it from the limit 0 to 2 pi, so you will end up with 0. And from the logic also, we can see that the force which is coming from the left side, or from this side or from the other side, both are balancing out each other. So there the net force would be 0 here. So but we can do it mathematically, just substituting the pressure at the surface of the cylinder from this expression put here and integrated over this theta from 0 to 360 degree, we are going to get 0. Same is true with the y component of the force. So here instead of a cos theta, I have a sin theta term in the y direction, and if integrated over the whole surface of the cylinder, I am going to get the resultant force in the y direction, and this resultant would come out to be 0 because Fy I have taken to be positive in the y direction. So by just a convention, that's why I have taken it, but this integral, the result, or you can think of logically, because sin theta is this curve. So area from 0 to 360 degree, one of the half is positive, other half is negative. So area under the curve from positive half and negative half, if you add them together, the result is 0. So you can see from the logic as well, this drag force is 0. But this is something which is strange. This result is predicting that the potential flow theory is unable to predict any drag. So it say there would be a 0 drag and 0 lift, because potential flow theory assumes that there is no rotationality, there is no viscous effect there. So it doesn't predict any drag. But if you just place a cylinder in front of a uniform flow, for example, if you just take your hand out from the window of a car, you always experiences a drag, and that is because of the viscous effect that is present in reality. But potential flow theory is unable to predict that. So the mathematical reason is the forces are in such a manner. The upward force is balanced by the downward forces, the rightward force is balanced by the leftward forces. So this is due to the symmetrical distribution of the pressure, the resultant force would be 0. That is actually due to the only due to the pressure. When we will do the external flow, we will learn that the drag has two components. One is due to the pressure force, pressure distribution, and other one is due to the viscous effect. Since in potential flow theory there is no viscous effects, only the pressure distribution is there, but pressure distribution is such that it is balancing out, so the net force come out to be 0. And this behavior, because in reality we always experiencing a drag over a cylinder. So this discrepancy is actually called as D'Ambert's paradox. So because due to the symmetrical distribution, the potential flow theory is unable to predict the drag force. Okay, and now we can come up with another superposition of the potential flow. Let's say we have a uniform flow, and if you sum up together with a source flow plus the sink flow. So can you imagine what will be equal to, what will be the resulting pattern when you combine uniform flow with the source flow? Keep in mind, earlier we have already done by combining uniform flow with the source flow, because fluid is coming from this direction, fluid is coming in the radial direction, and they cancels out. So this would be something combining these. We have already learned that it is sort of a half body. So can you predict now what will happen if you have a superposition of uniform flow, source flow, and sink flow as well? So take it a pause and try to answer this. Try to draw the flow pattern. Okay, I'll show you the answer now. So the answer would be that this would simulate something like you have a body shaped like this. So this point would be the origin of the source, and negative n is the strength of the sink. So it would be something flow over this shape of the body, and we have given a name called Rankine body. So just superimposing the uniform flow, source flow, and sink flow, you end up with the Rankine body. So as we already have done, combining source and sink in a particular manner to bring up a doublet, and when doublet combines with uniform flow, it is a flow over a cylinder. So don't be confused with flow over a cylinder with such a combination, because you are combining source and sink, but not with the definition of a doublet. Doublet is one particular condition under which the product of the strength and distance between them is approaching towards zero. Then the resulting pattern would be called as doublet. And doublet combined with uniform flow is actually flow over a cylinder. But this would be a different flow pattern. We call it a flow over a Rankine body. Okay, there is a problem, and that would help you to understand this behavior of flow over a Rankine body. So what I have done is I have taken a source of strength. Strength of the source is 10 meters square per second at location when x is 1, y is 0, and sink of the same strength with the same 10 meter per second square strength is placed at -1 when x is -1 and y is 0. So both source and sink are placed at a 2-unit distance. What I am doing is I am combining with a uniform flow of 25 meter per second in the negative x direction. So flow is coming from this direction, not from this direction. So, but the magnitude of the free stream velocity is 25 meters per second. Okay, so this is the problem, and let's see how the picture looks like. There is an origin. Source is placed at +10, sink is placed at -10, and there is a uniform speed coming of 25 meters per second from negative x direction. So so what I do here is, what I have to work out, I have to work out the size of the Rankine body. Size means the length and the width. This is something we have to work out, and the difference in pressure between a point far upstream in the uniform flow. So this is a uniform flow. I am just away from the uniform flow when I am at one distance and one distance. Somewhere here I have to work out the difference in the pressure between the free stream pressure and the uniform flow at that point. So first we will work out, before working out the pressure distribution, we have to work out the velocity distribution. So the first instance we will work out the length and the width of this Rankine body, and in the second part we will work on the pressure difference, and before pressure difference obviously we have to work out the velocity distribution, as we have seen that is required in the flow over a cylinder too. Okay, the first step is what would be the resulting stream function for this Rankine body, combining uniform flow, source flow and sink flow. Okay, according to this problem, the uniform flow is rectilinear. It is u infinity times y. So it is given as -25y. So u infinity is -25 because it is from this place. So that would be the stream function for uniform flow. And then we have a stream function m times theta, and m is q over 2 pi b. B is actually the width from which the flow is coming through the, so in this case B is 1, and here m is given in the units of meter square per second, and q has a unit of meter cube per second. So B should be in meter, and meter cancels out, so you have a unit of 10 meters per second square. So I can write here q 10 over 2 pi, B is 1, and because it is actually q over B is given here actually. So theta is I have put in terms of Cartesian coordinate system. So as I know, if my source was at origin, so r and theta would be that angle. So y over x would be the transformation, tangent inverse of yx would be the conversion from theta. Theta would be tangent inverse of y over x. But since here my source is at 1 unit to the right, So my corresponding function would be y over x minus 1. Similarly, I can work out expression for the sink, which is source is positive, so sink is negative, and the same thing is not at origin, somewhere at origin. So that would be the corresponding stream function for the sink. So the function for this Rankine body would be the summation of the uniform flow, the source flow, and the sink flow combined together to get the corresponding stream function for Rankine body. Okay, now see this. As we know, if we know the stream function, we can easily work out the velocity component in x direction by differentiating with respect to y. So if I differentiate with respect to y, so derivative with respect to y would be minus 25 here. So just differentiating this function with respect to y. Similarly, if you differentiate this, you are going to get these expressions. So I'm not going into the derivative part. You know, tangent inverse of x is something like 1 over 1 plus x squared, something like that. So the same formula you apply, you end up with this derivative. So that would be the velocity component in x direction. As you see in this diagram, at the stagnation point here, when obviously your y is 0 here, and your horizontal component would be 0 at the stagnation point, because there is no resultant speed at the stagnation point. So I just make it 0 here and y 0. So now I substitute u 0 and u is 0, and I have just substituted y 0. So y 0, then it is only x there. So y is 0 here. So that would be the equation expression for you have only unknown in this equation is x. So you simplify x, x comes out to be plus minus 1.062 meter. So x could be plus 1 or minus 1.062 meter from this point to this point. So that is actually the distance x1 and x2. So we can easily work out the length of the Rankine body would be, because we know the location x from origin to this stagnation point. So I know it is 1.062. So this is also 1.062, so it is twice of that. So the length of the Rankine body would be 2.124 meters. So first half of this problem, we have to work out the size of the Rankine body. So we have worked out the length. Now we have to work out this width. And as width y is changing, and there will be certain maximum value of y. Okay, so you need y component of the velocity, and y component of the velocity is minus dava psi by dava x. So differentiate with respect to x and make it obviously at this would be, if you differentiate with psi with respect to x, then 25 and y would act as a constant. So derivative of a constant would be 0 here. So I'm sorry, I have to put is a plus sign because the plus is here. So I have to, okay, no, not plus here, because minus is multiplying. So that's why you have a minus as a multiplier with v. So minus is here. Okay, so differentiate this with respect to x. Now y is not a constant, so you are differentiating with respect to x. The derivatives are this. As we know that there is a streamline which is at the surface of this Rankine body, and that stream function would be passing through these stagnation points. And we know that these at that point where y is maximum, your stream function would be actually corresponding stream function would be the stream function at the surface of this Rankine body, and that we are assuming it to be 0. The stream function we are assuming it to be 0, and since this streamline would act as a solid body, so there is no velocity in the y direction. So what I can take it, velocity in the y direction taken to be 0 and psi to be 0. So what I do is now I just substitute velocity to be 0 here, and then only unknown in this equation would be From this I have v to be made 0. So now I have this expression, only thing I have done is v0, and the whole thing is like the same. Now I need to simplify this because 2 pi over 10 would be 0, cancels out, and these two will be equal. As I know that y is not equal to 0, there is some y there, so it means these two equations would be equal. So y square cancels out. So what I end up with x0, because it is evident from the figure as well that the maximum y occurs when x is 0. You are at the origin. So what I need is to get the maximum value, I just substitute x equals to 0 in this stream function, so that I am assuming that that is at the body contour of the body, and earlier also the string function at the surface where the surface acts as a solid body and that surface is passing through the stagnation point. We are assuming that string function to be 0. So now substitute 0 here and x0. So what I end up with in this equation, this is 0 here, minus 25y, and all x to be 0. 0 here, so minus y comes here, 0 here, so plus y. So you have that expression. Now we know that since the magnitude of y is either if you go upward or downward, its magnitude remains the same. So what I do is I just make it a simplification, because it would be 2 tangent inverse of y. So I'm talking about only the magnitude of y. So I simplify here in this equation, the only unknown is y. So I just, because this is sort of a transcendental equation and it would be not so easy to work out, I have used ease to solve this. So this maximum value comes out to be 0.453 meter. So this thing is something like 2 meter something, and this one is 1 meter. So this distance is around about 0.453 meter. So width would be twice of that, it would be something like 0.906 meters. So that is the second part I have done. Okay, the next is to work out velocity distribution. So velocity distribution is simple, because as you know the velocity component, so what I have to calculate is at some point 1, because that is the point where I have to calculate pressure difference. I need velocity at that point as well. So velocity component at 1 would be just substituting x and y1 here. That comes out to be minus 25.63 meters. Similarly, I can work out the velocity component in the y direction. At this point, it comes out to be minus 1.27 meter. I can easily calculate the resultant of at 0.11. So using Bernoulli equation, I can find out the expression for the pressure at the free stream, the velocity at the free stream, pressure at 0.11, and velocity at 0.11. So this would be the velocity at 0.11. I just substituted that expression. So velocity at 1 is 25.66 and velocity at the free stream is 25. So I would be able to get, if I know the density, I can easily work out the difference between the pressure at the free stream minus the pressure at 0.11. So that is the part which actually the last part which you have to do in this problem. So in this way we finish this lecture today.